All right, in the next little bit of Chapter 22, we're going to take a slight detour away from electrophilic aromatic substitution and look at some kind of typical reactions that allow us to manipulate these substituents we're putting on the aromatic ring. They're pretty handy for synthetic purposes, if you know what I mean. So the three reactions that we're going to look at are a new oxidation, chewing up an alkyl group on an aromatic ring. That'll give you an aromatic acid. Reduction of the nitro group, so we put the nitro group on the aromatic ring and then we can reduce it down to the amine. And the third one is something called aryl diazonium ions, which is really cool, clever chemistry. Alright, the one we're going to focus on right now is the oxidation bit. And the whole deal is that I can take an aromatic anything, and it really doesn't matter what else is attached here. If I want to, I can pretty much activate that carbon and chomp up everything right down to that piece to get to that bit. Why can this happen? What's so special about that carbon, which is the benzoic carbon? Well, you remember that it's pretty easy to make a reactive center there. That's a very stable carbocation if we were to lose a leaving group, and it's a very stable radical if we were somehow or other to be able to form a radical at that position. So we're really not going to learn a mechanism because it's really not well understood, but it's probable that the mechanism somehow or other has something to do with a benzoic radical. We will use this opportunity to review oxidation. Basically, if we have alcohols, specifically a primary alcohol, plus one, minus, so we've got -1 oxidation state going up to +1 oxidation state at the aldehyde and +3. So we've got 2 steps of oxidation to go from an alcohol all the way up to the acid. Or we can oxidize alkenes and alkynes, for example, using a peroxy acid to epoxidize an alkene. But we've never seen a non-functional group molecule like an alkane get oxidized. All these other oxidations have been where there's already a functional group present. So how in the world can this happen? Well, it can happen because we use some kind of incredibly powerful oxidant like permanganate or chromium-6. I will, however, admit, and it's an interesting thing for you to think about, that cytochrome P450, if you've heard of that or seen that in your cell bio or other biology classes, cytochrome P450 is very specific at being able to oxidize hydrocarbons and basically remove a carbon-hydrogen bond and put an oxygen there. So that's pretty slick. But we humans in the beakers, we're not quite as adept at that. So we have to just beat the snot out of it with permanganate or chromium. So this is how it works. Isopropylbenzene, I take permanganate and acid and water, base and water. It could be acid and water, doesn't matter. You just chop everything off. So that gets chopped off, that gets chopped off. Like I said, it doesn't matter if you start out with isopropylbenzene, butylbenzene, whatever. You will end up going all the way down to the benzoic carbon and oxidizing it. Now, point about this is that this is a really bad way to do business in terms of green chemistry, because you're throwing away, in this particular example, you're throwing away 2 carbons that are going to go into the hazardous waste. A key principle of green chemistry is that you don't throw away any carbons. Maximize the incorporation of all materials into the final product. So it may be that you need to use this kind of chemistry, but it's not green by any stretch. It's wasteful. Alright, so that was an oxidation review. Now we're going to do a reduction review. So this is important chemistry because, as we've already alluded to, there's no real obvious way to put a nucleophile like NH2 onto a nucleophile. Nucleophile plus nucleophile equals no reaction. So a recap of reduction. Well, it's kind of the opposite of oxidation, right? So we're going here from +3 to, what was this? I think this was +1. I think this was -1. We got +2 down to 0. No, that's not right. It's not 0, it's -2, right? Because we're looking at that carbon right there that has 2 hydrogens attached. So, what do we use to do this? Well, I don't know what we use to do it yet. All I know is that what it amounts to is ripping off those oxygens somehow or other and replacing them with hydrogens. That's what reduction is in organic chemistry. Now we're going to do that where we rip the oxygens off of a nitro group and replace them with hydrogens. That is definitely a reduction. So now a review of the reducing agents. All of these guys, as you are well aware, are electrophiles. There's supposed to be a little plus there. Electrophile, electrophile. So no problem getting H- to add. Lithium aluminum hydride, dibutyl aluminum hydride, lithium tritert butoxide aluminum hydride, sodium borohydride, hydride. Okay, we also learned the magic chemistry associated with reducing the carbonyl completely off, replacing that with the 2 hydrogens via either the Wolff-Kishner or the Clemenson or Raney nickel, where you go through the thioketal and then add Raney nickel, and that reduces it all the way down to the hydrocarbon. Now we will see what we need to reduce a nitro group down to an amino group is a 0 valent metal. And you may think, well, you've not seen that before, but that would be incorrect because you have seen that before. The dissolving metal reduction of alkynes down to E-alkenes use 0 valent sodium metal in liquid ammonia. And this reaction, well, it's an oxidation, obviously, but for it to end up at the aldehyde stage, you have to use a reducing workup. And one of the options was to use something like zinc as your reducing agent in the workup so that it doesn't go to the acid. So that's exactly what's going to happen. We want to reduce the nitro group. We have many options. You really can't guess wrong. Pick a 0 valent metal, any 0 valent metal, and it's likely that it's going to reduce your nitro group. The one I typically have seen is tin, but I think Cardi uses zinc or iron. Notice that each of these are invariably followed up with a basic workup. You might want to think about why that would be the case. And as with the reduction of carbonyls, one option that you can use is the use of catalytic hydrogenation, and that works very neatly and cleanly. So the take-home message here is, if you think about the fact that this is a reduction, and you pick a reducing agent, it's likely to be correct because it's likely going to work to reduce your nitro group down to the amine. That's important because then we can use that amine to transform your aromatic compound into all kinds of other things, as we'll see in the next mini lecture. So we end with an important piece of advice for you. Everybody wants to save money. I have a surefire way for you to double your money, and that is by simply folding it over upon itself and putting it back in your wallet. Get it? You're folding it over on itself, so that's doubling it. Yeah, okay, that's enough. Enough of that. See you in class.